My name is Zhang Junyuan, and I come from Doshisha University. Today's presentation theme is Assisted Timing Decision Method for Well-Type Working Assist Suit by Hip Joint Angular Acceleration. In recent years, there is a need for devices that support the working of the elderly and encourage independent working. One of them is an assist suit that supports working by attaching a powered device to the user. A typical example of an assist suit is an Accele assist suit, which is assisted by driving a metal frame along a human skeleton with a motor attached to a joint. However, the Accele type has the disadvantage that it is necessary to align the joint position of the user with the Accele, and it is difficult to wear it for a long time due to its size and weight. In order to solve these problems, well-type suits like Himiko used in this study are being developed. Conventional assist timings were determined by the obtention of facility and joint torques, but these methods are difficult to set the optimal assist timing for each user. Therefore, in this study, we propose an assist timing decision method based on the result of the hip joint angular acceleration by the IMU sensor, using the well-type assist suit Himiko. As shown in the figure, Himiko is consists of main unit, the waist belt, knee belts, IMU sensor, and 4 wheels of 2 front wheels and 2 rear wheels. The user carries the main unit on his or her back and wears the waist belts and the knee belts on the upper knees. As the motor rotates, the wear tension between the waist belt and the knee belts are generated. The wear tension assists the movement of the hip joint by generating torque on the hip joint. In addition, the knee belts are equipped with IMU sensors, which are powered and communicated from the main unit, and it is possible to measure acceleration and angular velocity in the 3-axis direction. For Himiko, the user can use the application software to set the assist profile items, which can be set up for assist timing from T1 to T4 in a gait cycle. T1 is the starting point of tension exertion. T2 and T3 are the maximum tension exertion seconds, and T4 is the end point of tension exertion. This figure is an example of hip joint angular acceleration calculated. T1 and T4 are determined as the timing at both ends of the range where the standard deviation of angular acceleration doesn't reach 0. T2 and T3 are determined as the time when the value of the first derivative of the angular acceleration changes from positive to negative or negative to positive when the value of the angular acceleration is 300 or minus 400. In this study, the subjects were 3 healthy males. Subject XY was the first time in this experiment, and subject Z was an expert who had expressed at least 10 times before this experiment. Subject X did experiments under the condition which T2 is the same timings as T3. Like this Mountain type assist. Subject Y did experiments under the conditions which T2 is different from T3, like this trapezoid type assist. The subject Z did experiments under both conditions. This is an example of working condition. In this study, first perform a normal working without assistance, and the assist condition is created from the result of the hip joint angular acceleration. After that, work under each assist conditions. After activating the assist, subjects worked on the treadmill at a speed of 4.5 kilometers per hour for 20 seconds to get accustomed to the assist suit, and then measured for 60 seconds. The analysis target was 50 seconds, except the first and the last 5 seconds of each condition. Figures shows the measurement environment in this experiment. The floor rotation force of feet and the position were measured by a left-right separated treadmill, and the body position coordinates were measured from 57 optical markers placed at a predetermined position on the whole body by 10 cameras of the 3D real-time motion measurement system. The rotation variable was measured by the load cell attached to the end of wires. The sampling frequencies of force plate, motion capture, and the load cell are 1000 helens, hydrant helens, and 1000 helens respectively. From the measured body position coordinates, floor rotation force, and rotations, the hip joint angle and the hip joint torque were calculated using the human body simulation software DynaWorks V2. Next is the result and discussion. Because subject X and Y were beginners to the experiment, we worried about the credibility of the experimental results. We mainly discussed the results of subject Z. As shown in the figure, the y-axis shows the difference in the maximal hip extension angles for normal working among the subjects, and the x-axis shows the experimental conditions. And orange is a trapezoid type assist, green is a mountain type assist. We can find in the mountain type assist, the maximum extension angle didn't change much more than trapezoid type assist. For maximum hip flexion angles, it was increased in the direction of extensions for all assist conditions in the mountain type assist. It was found that when the maximal tension exertion seconds become longer, the assist influences the joint angle until sometimes has passed after the assist. In addition, when working with no change in joint angles is regarded as working with a natural gait. Mountain type assist is less likely to have an effect after assisting than trapezoid type assist, so it is working with a natural gait can be achieved. The y-axis shows the differences in the maximum extension torque for normal work among the subjects, and the x-axis show the experimental conditions. Comparing the trapezoid type assist of the expert with the mountain type assist of the expert. The mountain type assist had a great amount of torque reduction in all conditions. For maximum high flex torque, the trapezoid type assist increased in maximum flex torque for all assist conditions, while the mountain type assist decreased the maximum flex torque for the fourth assist and trials number 6 and 7. It was found that the torque decreased in almost all trials at the maximum extension torque, and the decrease in torque was larger with mountain type assistors than trapezoid type assistors, especially for the user who had experiences. It was also found that the torque decreased in some trials at the maximum flexion torque, and the decrease in torque was greater for the mountain assist than trapezoid assist. In this study, we propose a method to determine the assist timing and set the optimal assist timing for each user and evaluated the proposed method using chemical. The maximal hip joint extension angle and the max hip joint flex angle could be maintained close to normal working. At the same time, the hip extension torque and the hip flexion torque were reduced as compared to normal working. The mountain type assist method was found to be particularly effective. Thank you for your attention.